Routh Hurwitz criterion. Routh Hurwitz criterion. So this is also a piece of classical analysis, very beautiful. The proof is difficult and we will not cover it. Okay, so we will learn it as a procedure. All right. So let us say I have a polynomial which looks like this: a n s to the power n plus a n minus 1 s to the power n minus 1 plus dot 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 plus a1s plus a0 equals 0. We can take a0 greater than 0. Why is that? Because if a0 is equal to 0, then we will factor out s, that s equals 0 will be a root, and then we will be left with the task of finding the other roots. Okay, and we can take it to be positive when it is not 0, because if it is negative we will just multiply by -1 throughout and nothing will change. Okay, the roots will not change, all the coefficients will change sign. That's all that will happen. Very good. We are interested in this question: how many roots are in the right half plane? Okay. Now, of course, with modern tools like MATLAB, for example, if I say n equals rand n 1 7, so that represents a 6th order polynomial. Okay, this times s to the power 6 plus this times s to the power 5 plus this times s to the power 4, 3, 2, 1, and the constant. All right, now we can say n equals minus n, and then now that's positive. I can make that 1 also, but it doesn't matter. I can say in MATLAB roots of n, and here it tells me that there are 3 roots in the right half plane out of 6. Okay, now here is a function which is the Routh Hurwitz criterion is implemented in this MATLAB program, which I will send to you later. You can pause your video and look at it. This is the program. You can even write it yourself, and that will help you both understand MATLAB and implement the code. So maybe I will not send you the program, but here is what we will do. I will say Routh of n, and I will get an array. Okay, so I get this array here. This is called the Routh array, and you will see that this number starts negative, negative. There is a sign change, it becomes positive. There is another sign change, it becomes negative, and there is another sign change. So the number of sign changes in the first column is equal to the number of right half plane roots. Let's do it again, okay, so that you will see that this is actually a reliable thing. So, and then we will see what the procedure is. So let's say ninth order polynomial. Okay, now we will say roots, and you can see 1, 2, 3, 4, 5 roots in the right half plane. And then if I do Routh of n, I get a big array. Now negatives up to here, then 1 sign change, 2 sign changes, then from here 3 sign changes, 4 sign changes, 5 sign changes. So this is really remarkable. The number of sign changes you see in the first column is equal to the number of right half plane roots. This has to do with complex numbers and arguments, and it's a complicated proof. The proof we will not cover, but we will try to understand what the process is and what the procedure is and what the utility of it is. Okay, so with modern tools, finding the roots numerically, if the coefficients are known numerically, that is easy, that's not a problem. But sometimes we may have them analytically. We may have parameters in here, you know, like this may be a design parameter, this may be some k, and then this may be some p, and then in the pk plane we may try to understand where it is stable, you know, maybe it is stable here and unstable here or something. How do we figure that out? Well, Routh Hurwitz criterion may help us in such situations. Okay, so the way we will proceed is we will start with this coefficient and we will put it here. We will not write this one and take the next one. Okay, so we will have an minus 2, an minus 4, and in this way until we run out of coefficients. And over here we will write an minus 1, an minus 3, an minus 5, and in this way we will continue. Okay, so now consider for a moment, suppose n is 8, that means there are 9 terms over here. If there are 9 terms, then the first row will have 5 terms and this will have 4 terms. Okay, but if there are 10 terms, suppose n is 9, then there are 10 terms, then there will be 5 terms here and 5 terms here. Okay, so the upper row will have the same number as the lower row, or it will have 1 term more than the lower row, and then there will be zeros. We are not interested in that. Now we have to write this number here, and what this number is going to be is, I will label this like that. I will put a star here, I will put a square here, I'll put a triangle here, and I'll put a circle here. Then what this number is going to be is square, triangle, minus star, circle by square. I hope you realize what this is. This is really, if you take this 2 by 2 block, you calculate its determinant, take the negative of the determinant and divide by this one. That's what this number is. So this number is now filled. I have to put another number here, and for this I will need new symbols over here. So I will put this hash mark over here, and I will put a circle with a dot in it over here. Okay, so that number. So then what this number is square times hash minus star times circle with dot divided by square. And what that means, I hope you realize, is that this one here and this one here, you make a 2 by 2 matrix, you take the negative of the determinant of that and divide by this one. Okay, so in this way you continue, and at some point of course you will get zeros, and when you have zeros, nothing there, then you will get zeros over here. Okay, so once you do that, once you implement that calculation, then what we have is, let me just block it out here, just ignore this part here, and let's say we now have some b1, b2 and so on. Okay, now we have to put this element here, and what it will be is b1, I'm just going to repeat the calculation, b1 an minus 3 minus an minus 1 b2 by b1, that will go here. Okay, and then what will go here? Well, I have to write b3 here, and then what will go here is this one times this one minus this one times this one divided by this one. Same pattern. Okay, so that's the pattern. And sooner or later you will run into zeros. You know, at some point you will get a number here, a number here, another number here, and a 0 here, and all zeros over here, you see. And when that happens, then you will have over here, you will have star delta minus hash times 0 by star, and that of course is just delta. Okay, and then after that, of course, because these are zeros, you'll just get zeros. Okay, so this line will become delta and your array will terminate. Okay, and you make this array, then you see the first column, and see the number of sign changes equals number of right half plane roots. So this is quite wonderful. Let's go back to MATLAB and see how that works. You have seen it for two polynomials over here. Now let me say n is equal to 1, 2, 3, 4, 5, 6. Okay, now there's nothing special about this. I can look at the roots. You see there are no purely imaginary roots. There are two right half plane roots, but when I try Routh n, I get some trouble because I get division by 0 and so on. We will understand that later, but you see the polynomial here is 1, 2, 3, 4, 5, 6. Those are the coefficients. So this is s to the power 5 plus 2s to the power 4 plus 3s cubed 4s square 5s plus 6. Okay, you come here. What should this be? This should be 2 times 3, that is 6, minus 4 divided by 2, that is 2 divided by 2, so it's 1. This should be 2 times 5, that's 10, minus 6, so that's 4, divided by 2, so that's 2. After that those are zeros, so this has become 0. Now we come here. What should it be? It should be 1 times 4 minus 4 divided by 1, so that's 0. What should this be? It should be 1 times 6 minus 2, so that's 6, divided by 1, so that's 6. I come here, what do I get? I get 0 times 2 minus 6 divided by 0. That is why I have infinity. Okay, so this infinity can be disturbed by changing it. So what I will do is I will say n1 is equal to n plus rand n. I just want to show you the size of n times 1e minus 8. So I'm just perturbing n very, very slightly. Okay, so if I do format long, and if I look at n1, you will see that they are perturbed many decimal places down. Okay, if you look at roots n and you look at roots n1, they are only slightly perturbed, right? I mean, these roots and these roots are very close to each other. 4634, 4638, 491797, 7984, 7988. You see, slightly perturbed only. But now when I try Routh n1, you will see that this has become well behaved. Okay, well, this is still 0. This is still 0 to this order, but what I can do is I can say format short e, just to clean it up a bit. Okay, and now you see this is better. So you see positive, 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 one sign change, another sign change. Okay, this number is very small, this number is very big, but the numbers are there, and you see two sign changes. You may think that this is random because after all I did a random perturbation. So let me do it again. Okay, so let me perturb and say Routh n1. So I'm perturbing n again randomly. Okay, and this is rand n, so positive and negative both are there. You see two sign changes. Let's do it again. Two sign changes, two sign changes, and two sign changes, and two sign changes every time. This is robust. That is because the roots are robust. Okay, but I may have a different situation. Okay, the different situation is, for example, I may have let me see now, n equals 1, 0, 3, 0, 2. What are the roots of this? So you see now there are 4 roots and all 4 roots are on the imaginary axis. Okay, so this is really a problem. When I try root n, I should get into trouble, and I do. You see, I get none, none, and none over here. It doesn't know what it's doing, right? But if I now say n1, if I'm perturbing it, you see, so now I get 2 sign changes. 2 of the roots went to the right, 2 went to the left. I do this again. This time I get 2 sign changes again. Let's do this 2, 2. Should be possible to you see, 2 to the right and 2 to the left, right? So but it should be possible to change it in such a way that all move to the left. Let's try rand and see. Well, there you go. Now nothing is in the right half plane. Very small perturbation still, right? N1 is still very small perturbation, 10 to the minus 10, 10 to the minus 9. But you see now all the roots are in the left half plane. All the roots are in the left half plane. Okay, so it's possible to perturb it slightly so that it goes all to the left half plane. It's possible to perturb it slightly so that they all go to the right half plane, right? I think this may work. We'll try our luck and see. You see, so one sign change, another sign change, another sign change, another sign change. 4 roots in the right half plane. When I look at the roots, all 4 are in the right half plane. Okay, the real parts are positive. So let's summarize. When we have the Routh array and we get some zeros and infinities, if under small perturbation the number of sign changes is robust, this means that the number of right half plane roots is actually robust, but occasionally because the coefficients are a certain way, you may get these zeros and infinities and 0 by 0 and so on in the Routh array. But if there are roots that are exactly on the imaginary axis, then you will also get this kind of funny zeros, infinities and so on, but they will be sensitive to the nature of the perturbation. Alright, this particular part would have been very important at a time when you were proceeding purely analytically. But now, because we are proceeding with a computer available and we are doing symbolic work, for symbolic work this is not so important. So let me show you how that works out. Okay, so let us say we have s cube plus a 2 s square plus a1s plus a0 equals 0. See, I have taken this coefficient to be 1. Okay, now what are the conditions on a0, a1 and a2 so that everything, all the roots are in the left half plane? Compare with s square plus a1s plus a0 equals 0. From your mechanical engineering damped oscillator experience, you know that if a0 is greater than 0, a1 is greater than 0, this will work. Okay, let's do a quick Routh array of this one. We will get 1, a0, a1, 0, and as we discussed, because this is 0, this one comes as a0 and this becomes 0. This is the Routh array. Very easy calculation. And because this has started as 1, we don't want a sign change, therefore we want this to be greater than 0, and we still don't want a sign change, so we want this to be greater than 0, and that guarantees that the 2 roots of this equation are in the right half plane. For the cubic, little more interesting. Okay, so we will have 1, a1, a2, a0. Okay, so what comes here? You know what, let me do something here, make it a bit easier. 1, a1, a0. Let me spread it out. Okay, so now this is going to be a2, a1 minus a0 by a2. Okay, that's here. Over here these are zeros, so this is 0, and then because this is 0, this one comes down here, and so this is a0 and this is 0. That's the Routh array. Alright, so now I don't want a sign change, right, because this is already 1. That means I want this to be greater than 0, I want this to be greater than 0, and I want this to be greater than 0. But of course, because this is greater than 0, I can drop this one from consideration, and so I have a0 greater than 0, a2 greater than 0, and a2 a1 greater than a0. These are the conditions that I have for a cubic. You can similarly do a fourth order polynomial, for example, and if you look on the Wikipedia page, that one is worked out, so you can see that to understand how it works. Okay, now consider this. Suppose I have s to the power 5 plus 3s to the power 4 plus ks square plus s plus k plus 3 equals 0. Okay, and I say, are there any values of k for which all roots are in the left half plane? You see, and this question can be answered in many ways. I mean, we can answer this using MATLAB as well, right? So let's go to MATLAB and see how we would do that in MATLAB. 1, 3, k, 1 and k plus 3. Okay, so what we will do is we will say kk equals linspace, let's say minus 10, 10, 400. Okay, then I will say for n equals 1 to 400, k equals kkn, p equals 1, 3, k, one k plus 3, c equals max real roots of p. This should be c of n, end. Well, that didn't work. That didn't work because I put a full stop there. Okay, now let me plot kk and c. You see, so well, in this range there is always a positive root, so it didn't work. Okay, all right, let's try once more. Kk equals, let us say 100. Well, it's only asymptotically approaching 0. So this is one where we didn't get such a nice result. There is simply no value of k for which all the roots are in the left half plane. Fine, that's fine. Let's go back here and look at this one using Routh Hurwitz or Routh Hurwitz. Okay, so we will have, from here we will have 1, from here we will have k, from here we will have k plus 3, from here we will have 3, from here we will have 1, and here we will have 0. Alright, let's make the Routh array. So that is 3k minus 2 by 3. 3k minus 2 by 3. This needs to be greater than 0. This one over here, this times that minus 0 by this is just going to be k plus 3 and 0. Very good. Then we will have one more, right, and that one will be let's see now, it will be 3k minus 2 by 3 minus 3 times k plus 3, the whole thing by 3k minus 2 by 3. So this expression is a bit big, but it is in this spot. Okay, now for the next one, of course we will just have 0, because this time 0, this time 0. So that's all we'll have. And then after that, let us simplify this expression here a bit. So we will have k minus 2/3 minus 3k minus 9 by 3k minus 2 over 3. Okay, that's what we'll have. So that will be minus 2k minus, this is 27, 29 by 3 over this times 3 over 3k minus 2. Okay, so let this number be hash here. So I will erase this part, and if I have not made a mistake, that's what we have there. You can meanwhile check the algebra here. If I have made a mistake, you'll need to correct it. Okay, so this number here is hash here, and then this 0 I'm sorry, hold on, this number here is this hash here, and then this 0 means k plus 3. Okay, very good. Now if you look at it, you will see for this is 1, this is positive, this is positive, and so we require this to be positive. That means 3k minus 2, I should not write here, this means 3k minus 2 greater than 0. That means k is greater than 2/3. Okay, over here I have k plus 3 greater than 0. That means k is greater than minus 3. This does not add new information. This is the binding one. Okay, and then I have here, so if k is greater than 2/3, that means 3k minus 2 is positive, and over here k is greater than 2/3, so that's positive. That means this is negative, this is negative, and so you see that it is not possible. This is less than 0. Okay, so not possible. Okay, that's a demonstration of the Routh Hurwitz criterion. Let me just check a little what the time is. There was a time. Oh well. Okay, so I think I will stop here and leave you with problems of this nature which you can think about. So for example, suppose I have g of s is equal to, s minus 2 by s square minus s plus 7. Okay, and then I have c of s as s plus a over s plus b. All right, and then what I do is I have a closed loop transfer function which is kcg over 1 plus kcg. And what that means is I have, let's see now, what I have is in the denominator I will have s square minus s plus 7 times s plus b plus k s plus a times s minus 2. I hope that is clear. That is because I will have 1 plus k s plus a over s plus b times s minus 2 over s square minus s plus 7, right? That's what I'll have here. This is G, this is C, and that's K. Okay, so now you see I have K, A and B. I can expand this polynomial out. I'll have s cube minus s square plus 7s plus bs square minus bs plus 7b plus etc. Okay, and then you could potentially use the Routh Hurwitz criterion to seek regimes KAB for which the system is stable. Okay, this is a hypothetical example. I'm not saying that you will find it easily, whether it is stabilizable or not. We are not talking about that. Okay, now let's just take about a minute to go over this code once again. So the coefficients are coming in. I am arranging them in a row. I am making the last one positive. Here is the length of A. Here is half length. If the half length is not an integer, in that case you add half to it. You start with an initialized 0 Routh array. Then in the first row you put, the elements of A starting from 1 but skipping 1, right? Every second, first, third, fifth and so on. And then S is the length of that, and then you go, that length you put in the second row, right? Let's see, length of that, because it could be the same as this length or it could be one less. I think that is why I use that. And now we are constructing it. So from the third row onwards we are inserting the places, and each time you are looking at the column, you think it is going from 2 to m, but actually I'm inserting k minus 1. Here is the negative, here is the determinant, here is the element from the previous column, previous row, first column. Okay, so that is how the Routh array is constructed. Alright, I will give you an assignment on this at some point.